atau sebaliknya.
Okay, hi, Assalamualaikum warahmatullahi ta'ala wabarakatuh. So this is chapter 2 for vector calculus. This is actually application of vector calculus. We have three theorem, Green's theorem, Stokes theorem, and also Gauss theorem, which actually will apply the method that you have learned in chapter 1, basically the triple integral, single integral, and also double integral, as well as the curl, gradient, and also divergent. Alright, so let us start with the Green theorem. So basically, for definition, let C be a simply connected piecewise smooth closed curve with a counterclockwise orientation which bounded a region located on two-dimension plane. So two-dimension planes means that the plane occurs on the xy plane. So now, in Green's theorem, we will consider the curve which only occurs in xy plane, and the curve has to be simply connected piecewise. As you can see here, we have C1, C2, C3, different curve where it actually can be called as piecewise curve. Okay, C1, C2, C3, different curve, but the curve is connected and also close. So it close the region. Let's say this region I call as B. Okay, so the combination of these three curve has closed this region D. Okay, and the row you can see the arrow here. The arrow here is counterclockwise. So means that if we have an object move on this curve, the object has to be moved in the counterclockwise orientation. Alright, so the keyword here is the curve has to be connected, has to be close, and also counterclockwise orientation. And one more thing, the curve has to be occurs on the xy plane only. Alright, so now, so based on these properties of the curve involved in the Green's theorem, so we will have a vector f pxy and also qxy, pi plus qj, and the Green's theorem defined that the line integral of p dx plus q dy is equal to the double integral del q over del x minus del p dy dx. So what we can say that the Green's theorem actually states the relationship between line integral and surface integral over a simply connected two-dimension plane. So the single integration here actually based on the line integral, and this double integral will apply the surface integral. Alright. So how to relate the Green's theorem, this Green's theorem with the line and surface integral? Okay, let me explain one by one. Okay, so we have this Green's theorem. So you can see the right hand side here, the left hand side here. Okay, we have this single integration. You can see this C means the curve, and this symbol actually means that the curve has to be closed curve. And actually, some book have arrow here, because they want to show that the curve has to be counterclockwise. Alright, so pdx plus qdy is actually based on the line integral f dot dr. Okay, but why it suddenly changed to be pdx plus qdy when we let f a vector to be pi plus qj, and the dr, as you know, is dxi plus dyj. You can see here we only consider I and j, component I and j, because this curve, the vector is only occurs on the xy plane, two-dimension plane. Alright, so based on the line integral f dot dr, pi plus qj dot dxi plus dyj, so we obtain p dx plus q dy. So obviously, this p dx plus q dy is based on the f dot dr. Alright, how about the other side? Right hand side. The right hand side, where it involves the double integral, this is actually obtained based on the surface integral, but by adapting the curl f here. Okay, so the original surface integral, as as you remember, if you still remember, we use double integral f dot nds, but now we have to adapt with the operator curl. But why we have to involve curl f? If you remember, we have learned in del operator, curl f is actually the rotation, the total circulation or the total rotation of a vector. So let's say we have a closed curve. Okay, this is C, okay, which counterclockwise orientation. So this C has closed a region. Let's say here we have region B. Okay, so we have actually a vector inside this curve. Okay, on this region we have vector where the vector is also rotate counterclockwise. Okay, so we have a lot of vector inside this region. So the total of rotation, the total circulation of the vector on this region is actually equivalent to the line integral of the C, where the C is the curve which bounded the region. Okay, so let me repeat. The line integral of this C is equivalent to the total circulation or the total rotation of the vector f inside the region D. Okay, so the line integral can be defined by p dx plus q dy, while the total circulation can be defined by using curl f dot nds by using based on the double integration. Alright, so now from curl f dot nds, y is moved, it's changed to be del q del x minus del p del y. Okay, so as we know previously, I mentioned that f is equal to pi plus qj, right? So now we use curl f. Okay, we know that curl f is ijk like this. This is curl f. So the function is pi qj, so z is equal to 0. So you find curl f, you will get this. Okay, I hope everybody still remember how to find curl f. And then find n. Curl f already find, now find n. Okay, now n. N, as you know, we have two ways to find n, right? If you still remember, we have two ways to find n. The one is by using gradient s over magnitude gradient s. This one is only for what? Cylinder and sphere. X squared plus y squared equal to r squared, and then also x squared plus y squared plus z squared equal to r squared. And the other one we base on the table 2.4, right? And this one, if you have a curve, a plane with a non-parametric surface. So now, since the plane that involved in the Green's theorem is in two dimension, so we should understand that the equation is always have z equal to 0. The equation of plane always z equal to 0. Okay, because it's in two dimension, we have any equation in terms of x and y, thus z is always equal to 0 in all cases. Alright, so due to the special case of Green's theorem, okay, alright, before that, we know now the surface or the plane is z equal to 0. So z equal to 0, we have one of the equation under table 2.4. Okay, z equal to 0, z equal to gxy, if you still remember, one of the equation under table 2.4. Alright, so we understood that we will use the column of z. Okay, so due to the special case of the Green's theorem, we know that the orientation of curves is only counterclockwise. So now, because we want to know whether the normal vector is positive or negative in order to use the formula of n. Now we know that because of C is always counterclockwise, so the normal vector is positive. Right. So positive, we have to use this formula. Alright, so partial differentiate the function of z equal to 0 equal to respect to x is 0, respect to y also 0. So we just have n equal to k. Now you find curl f dot n, and then you will get this formula. Okay. This is actually I want to show how the formula of Green's theorem is obtained, because I mentioned to you, I told you that curve, this one, the del x minus del p del y, is based on the curl f dot n. So now I derived to you, I've shown you how this equation is based on the curl f dot n. So now hopefully you understand why this how the equation is obtained. Alright, so now I have already shown you that the single integration p dx plus q dy is based on this f dot n f dot dr of the line integral, and then the right hand side, the double integral curl del q del x minus del p y is based on the curl f dot n ds, where ds can be dy dx, can be dx dy, can be r dr d theta, where it's based on the condition given in the question. Alright, so I will proceed in the next videos for the example. Okay, thank you. Alright, Bismillahirrahmanirrahim. Okay, before I discuss, before I explain the example on the Green's theorem, I want to tell you that for Green's theorem, we have a few, we have two types of question. Question sometimes can ask you to, to prove the theorem. Okay, the theorem. You have to show that the right hand side, the left hand side is equivalent to the right hand side. You have to solve both sides, and you have to make sure your answer for left hand side and right hand side are same. Sometimes question also can ask you to use the theorem. Okay? To use the theorem means that you have to do whether left hand side or right hand side. Okay? Okay, now let us move to the example 1. Alright, question 1 asks you to show that the Green's theorem is verified. It's verified for the single integration cxy plus y squared dx plus x squared dy, where c is bounded by y equal to x and y equal to x squared. Sketch the curve C. Alright, so before we start, okay, you have to know, you have to compare this equation C with the p dx plus q dy. Okay, the left hand side p dx plus q dy. So you can see here, this is obviously as p, this is obviously as q. The xy plus y squared is the p, okay, this is the p, and then the x squared is q. Okay, now start sketch the curve. Okay, okay, let me sketch it for you. Remember, when you do the Green's theorem, you don't have to worry, because the curve is only occurs on the xy plane. Right. So what is y equal to x? The curve, a straight line curve, intersect at x equal to 0, y equal to 0. Right. This is y equal to x. And then y equal to x squared is a quadratic equation. Okay, something like this. Maybe sorry for what not my sketching is not so good. Alright, don't worry. We just want to show that this is y equal to x squared, and this one is y equal to x. Okay, maybe you can directly write this is as the C1 and this is as the C2. You don't have to worry, you can choose this y equal to x as a C1 or this one as C1, it's up to you, as long as we name it, because we want to do it one by one after this. Now I do arrow. I made an arrow, two arrows for each curve, an arrow for each curve, and you have to remember the arrow has to be counterclockwise. Okay, right? So you sketch, you name each curve. Okay, you have to make sure both curve is close each other. It's close a region. We have a close region here. Okay, we have a close region. So we have name each curve as a C1 and C2, and the curve has to be counterclockwise. Right, now find the intersection point. We have intersection point here and here. Okay, we have intersection point. I know everybody know this is 0, 0. So what is the intersection point of here? Alright, so how to find the intersection point? You do the simultaneous equation. We have y equal to x squared and also y equal to x. Okay, because the point here is the intersection of the y equal to x and y equal to x squared. Alright, so now I substitute this equal to equation 1. So I have x squared equal to x. So x squared minus x equal to 0. Can you find it? So it is x minus 1 equal to 0. Okay, factorize it. So you have x equal to 0 and also x equal to 1. Okay, so if now if x equal to 0, what is y? Y is also equal to 0 because we have y equal to x here. Okay, so when x equal to 1, y also equal to 1. So means that we have 2 points 0, 0 and also 1, 1. So 0, 0 is here. So point here is 1, 1. Alright, now clear, right? Okay, now we want to start which part first? We already sketched it. Now we're going to solve it. Maybe I want to start with the left hand side, this one. Remember, the question asks you to show that the Cruz theorem is verified, so you have to show both sides. The p dx plus p dy is equal to the double integral del q del x minus del p del y, dy dx or dx dy. Okay, depends on the condition. Alright, now I want to start with the left hand side p dx plus p dy. So now remember, this is line integral. This one line integral p dx plus q dy is a line integral, right? So you have to solve the p dx plus q dy for each curve because we have two curves. You have to do for both curve and the final answer will be end up together. Alright. So C1, I will start with the C1. C1 is equal to y equal to x squared. Okay, C1 is equal to y equal to x squared. Remember, the first step in doing the line integral is parameterize the equation. So you have to parameterize y equal to x squared. What you have to do is you take x equal to t, therefore y is equal to t squared. Remember this? Here you do the parameterization equation, the first step of line integral. Now what you have to do is substitute both equations into p dx plus dy. Okay, so you have x, y. X is equal to t, y equal to t squared, and then plus with y squared to t squared power of 2. And what is the x? Here we have the x. So you have to find the x here. So the x is differentiate x, you get dt. Differentiate y, you get dy is 2t dt. Alright, so dt, you can write dt here plus x squared. X squared is t squared, dy is 2t dt. Okay, alright, so you can simplify this. You'll get t cubed plus t power of 4 plus 2t cubed, and overall is respectivity. Okay, alright, next slide. So before this we have t cubed plus t4 plus 2t cubed dt. And then you can simplify it, you get 3t cubed plus t power of 4. Okay, now you want to determine the limit. Alright, let me sketch it again to you. We have y and x. We have two curves here. Okay, point here. This is the C1 that you integrate now. You solve now. So here is 1, 1. Here is 0, 0. the arrow is oriented counterclockwise. Okay, this is C1. Alright, so now the limit. Remember how to determine limit for line integral. Okay, we we have the parameterization equation x equal to t and y equal to t squared. Remember, I told you in the line integral how to determine limit is based on the equation that you have declared as t. Okay, you take x equal to t in the first step of the parameter of this solution parameterize the equation. You take x equal to t so that the limit will be based on the point of x. So the arrow is from this point to this point, right? So counterclockwise. So of course the limit will be from 0 to 1. 0 to 1. Be careful here. It has to be counterclockwise and it has to be based on the function, on the point that you have declared as equal to t. Yang mana you ambil equal to t tu, yang tu akan jadi limit dia. Okay? So limit of x is taken because the point of x is taken as the limit because we have put x equal to t. Okay? Alright, now you integrate it. 3 t power of 4 over 4 plus t power of 5 over 5, 0 to 1, substitute it, you will get 19 over 20. Alright, so this is C1. Now proceed to C2. C2, we have y equal to x. Okay, parameterize it. What you have is x equal to t. So y will be also equal to t because we have take x equal to t, y also equal to t. Okay, alright, now substitute into the p dx plus q dy. So x is equal to t, y is equal to t as well, plus y squared t squared. Okay, and then dx is what? Okay, differentiate it, you will get dt, right? Differentiate y is also dt, dx is dt. Okay, and then x squared is t squared, dy also dt. You can add together t squared plus t squared plus t squared dt. So this is equal to 3t squared dt. Now the limit for this curve C2. Okay, C2, the arrow is from point 11 to the point 00. Point 11 to the point 00. Can you see it? The point 11, this is 11 to the point 00. This is because the arrow is counterclockwise. Now, which point you want to take as the limit? You can choose x or you can choose y because both of them are equal to t, right? So now the limit will be 1 to 0 because the arrow is counterclockwise from 11 to 00. Now you integrate it, the 3t cubed over 3, 1 to 0, you will get negative 1, negative 1. Therefore, C1 plus C2 is equal to 19 over 20 minus 1 plus negative 1. So it is equal to negative 1 over 20. So this is at the left hand side. How about the right hand side? Okay, let us proceed. Now we're going to solve the right hand side. The double integral del q del x minus del p del y. Okay, of course, for this question, we will solve dy dx or dx dy. Alright. Now, first of all, you have to know what is p, what is q. Okay, what is p and also what is q because we want to find the partial differential of this. So based on the step 1 just now, we know that p is equal to xy plus y squared, q is equal to x squared. So partial differentiate p respect to y based on the function here, based on the formula given here. So it is x plus 2y. Del q del x is equal to 2x. Now your del q del x minus del p del y is equal to x plus 2, it is 2x minus x plus 2y. So it is equal to 2x minus x minus 2y. So equal to x minus y. Okay. So now we're going to integrate x minus 2y. Okay, I want to choose dy dx. Okay, so how to determine the limit? Let me sketch the figure again. Okay, we have two curves which close each other. This is y equal to x squared. This is y equal to x. Alright. We want to choose dy dx. So determine the limit of y first. Okay, listen here. Which figure is below? Which figure is below? So figure y, the curve, which curve is below than the other curve? So you can see obviously here, the curve y equal to x squared is here, right? Y equal to x squared is here. Y equal to x squared. This is the below figure, which is below than y equal to x. So y equal to x squared will be the lower limit, and the upper limit, you can see this is upper than y equal to x squared, so the upper limit is y equal to x. Okay, again, which curve is below than the other curve? It is x squared, right? X squared is below than y equal to x, so x squared will be lower limit, then x will be upper limit, and then the limit of x have to take the smallest point of x. Remember, point of x just now we find here is 0 0 and point here is 1 1. Which point is smaller? The point of x is smaller, it is 0, and the bigger point of x is 1. Okay, so now you integrate. Okay, remember this one has to be in function, this one has to be in point. Okay, so now integrate it. X y minus 2y squared over 2 x squared x dx, and 0 1 here. You substitute the limit and you get x minus x squared minus x squared minus plus x squared power of 2, x squared power of 2, and then you solve it. Next, proceed. So this now we get 0 1 x minus x squared minus x squared, minus is plus x squared power of 2 dx. Okay, so simplify it, you get x squared minus x cubed plus x power of 4 dx. So you will get x cubed. So now integrate respect to x, you get negative x power of 4 over 4, because this is already 0, plus x power of 5 over 5, 0 to 1. So you will get what? Negative 1 over 4 plus 1 over 5. So the answer is negative 1 over 20. Alright. So now the left hand side just now, which is del q, which is p dx plus q dy, we obtain negative 1 over 20, and the right hand side, which is the double integral del q del x minus del p del y dy dx, also obtain negative 1 over 20. Therefore, we we can say that the Green's theorem is true. Alright, hopefully you are clear on this. We can move to the next example. Thank you. Alright, Bismillahirrahmanirrahim. Okay, remember in example 1 just now, we have uh, solved, we have done the proving. We do the proving where we have shown that the left hand side is equivalent to the right hand side. Now this is in example 1. Now for example 2, I want to show how you can just use one of the formula where the right hand side or left hand side where it depends on the question. So in the examples 2, we just want to use the theorem, Green's theorem. Okay, let us proceed to the question. So question said, use the Green's theorem for solving x squared plus y squared dx plus x plus 2y dy. So you're going to use Green's theorem to solve the p dx plus q dy. This is actually p dx plus q dy. Okay, we're going to solve p dx plus q dy using Green's theorem. Okay, which has been evaluated by boundary that defined by x equal to 0, y equal to 0, and x squared plus y squared to 4 in the first quarter. Okay, so first of all, as usual, we're going to sketch the figure. Sketch it, okay, only in two dimension. Okay, so x equal to 0, x equal to 0 is a curve, is a line on the y-axis. So this is x equal to 0. Y equal to 0 is a line on the x-axis. This is y equal to 0. Okay, and then x squared plus y squared equal to 4 is a circle, and they say that in the first quarter only. So this is the first quarter. So this is x squared plus y squared equal to 4. So we have a closed curve here. Okay, C1, C2, C3, counterclockwise. Alright, so now we have three curves altogether, but read the question again. Use the Green's theorem for solving p dx plus p dy. Okay, use Green's theorem. Green's theorem said p dx plus q dy equal to the double integral del q del x minus del p del y. This is based on the Green's theorem. Green's theorem said solve these using Green's theorem. So what you have to do is solve this part, okay, because you are using Green's theorem to solve this, so you have to do the other side because you are using Green's theorem. If you're still using this equation to solve this problem, you're actually not using the Green's theorem. Okay, let me repeat. Use the Green's theorem to solve p dx plus q dy. So in your solution, you have to do the other side. Okay, is it clear? Alright, let me proceed. Okay, so now you are going to do del q del x minus del p del y. Now you're going to do del p del x plus del q del y. So you have to know what is your p and what is your q. So p in this case is x squared plus y squared. Q is x plus 2y. Okay, then find del p del y and del q del x. Del p del y is 2y, del q del x is 1. Okay, alright, so p is x squared plus y squared, del p del y is equal to y, q is equal to x plus 2y, so del q del x equal to 1. Therefore, del q del x minus del p del y is equal to 1 minus y. Okay. So next is going to integrate the 1 minus 2y dy dx. Okay, dy dx or dx dy or what? Okay, now we have to base on the on the on the plane that we have just now. Okay, we have first quarter circle, right? We have y equal to 0 here, we have x equal to 0, and also we have x squared plus y squared equal to 4. We know that the point here is 2, 0, and point here is 0, 2, right? Because radius is 2. Okay, now, so this is first octant circle, first quarter circle. So obviously, you have to use polar coordinate of circle or polar coordinate of plane to solve this. Okay, otherwise your integration will be harder. Okay, so now we're going to use polar coordinate of plane. We know that x is equal to r cos t, or you want to use r cos theta, it's up to you. Y equal to r sin theta, and now your ds, which is dy dx, will be changed to be r dr d theta. Okay, now it will be 1 minus 2 r sin theta, and dy dx will be r dr d theta. Is it clear? Okay, because this is first octant circle. So you're going to do double integral. So you have to use polar coordinate of plane so that your integration will be easier. Okay, let me simplify this. You expand, you will get r minus 2r squared sine theta dr d theta. Okay, now limit. How about the limit? Radius, very easy. It is 0 to 2. You understood already, right? Because based on the radius is 2. The theta is 0 to pi over 2 because it's a first octant circle. Okay. So now integrate respect the r. Okay, r squared over 2 minus 2r cubed over 3 sine theta 0 to 2 theta. Okay, substitute the limit of 2, you will get is 2 minus 16 over 3 sine theta d theta. Now integrate respect to theta, you will get 2 theta minus integrate sign is negative cos, so it is plus 16 over 3 cos theta 0 to pi over 2, and then you substitute the limit, you will get the final answer is pi minus 16 over 3. So this is the final answer. You don't have to do the other side because the question tells us you to use the Green's theorem to solve the pdx plus dy, so you have to do the double integral. Okay, so now you can see that the Green's theorem is actually let you to simplify the solution. Okay, instead of you have to use the single integration, the line integral to solve each curve C1, C2, C3, because we have 3 C here, C1, C2, C3, but now you can do the integration one time only, where you integrate this the region here. You integrate the region, the double integral simultaneous in one time only. So the integration will be simpler, and the Green's theorem is complete. Okay, so that's all. Thank you. Hopefully it's clear. Example 1 and example 2. So you just can proceed it to tutorial. Thank you for me. Assalamualaikum.
Tanah yang basah berwarna